to Russian for the first portion. Да, всем добрый день, спасибо, что присоединились. Вот как сказал Джипенко, который представляет компанию Huawei вот в работе с комьюнити во всем мире, мы решили организовать в России сообщество вокруг MindSpore. MindSpore, я надеюсь, вы, может быть, посмотрели. Это фреймворк, созданный Huawei, open source фреймворк, который был выпущен где-то в марте этого года и начал активно развиваться. Вот, и мы хотим очень сформировать активное сообщество в России вокруг этого интересного проекта. И сегодня я сделаю небольшой introduction минут на 15 по-русски, и потом еще один наш коллега из Китая, Леон Ванг, расскажет про то, как другой очень интересный open source проект TVM используется внутри MindSpore для того, чтобы обеспечить максимальный перформанс. Вот. Буквально еще два слова. Не буду скрывать, что для нас в России это тоже новый продукт, и буду откровенен, что многие сотрудники, в том числе я, достаточно недавно находятся в компании, то есть я, например, 3 месяца присоединился, кто-то там чуть больше, вот, но тем не менее нам кажется, что этот проект очень интересен, он включает в себя много инноваций, как таких сугубо академических, так и индустриальных, оптимизационных. Вот, поэтому мы хотим активно начать про него рассказывать, организовывать различные мероприятия, хакатоны, конкурсы, с тем, чтобы это стало инструментом, который вы пользуетесь, и в идеале проектом, в который вы контрибьютите. Я расскажу про возможности, которые компания Huawei предоставит для этого. В целом, вот на этом слайде я хотел бы остановиться на роли MindSpore в экосистеме искусственного интеллекта для платформ Huawei. Во-первых, если вы вдруг не знаете, что у Huawei есть своя архитектура NPU-чипа для Artificial Intelligence с мощными возможностями там, матричных вычислений, векторных, скалярных, и все это на одном чипе и в различных форм-факторах. Это все в разных платформах распространяется, от телефонов, embedded устройств, IoT-девайсов до использования в мощных кластерах. Соответственно, сверху этого выстраивается софтварный стек, там на первом уровне, это понятно, какие-то low-level там firmware, которые осуществляют доступ к этому железу, а сверху этого enable'ится вся экосистема тулов, чтобы сделать удобный доступ для всех участников комьюнити, дейта-сайентистов и embedded инженеров, и тех, кто уже деплойментом занимается. Соответственно, логично выглядит то, что такие популярные фреймворки, как TensorFlow, PyTorch и остальные, например, Paddle, которые в Китае тоже активно используются, они оптимизируются, то есть туда добавляется код, который позволяет запускаться на платформах от Huawei, запускать тренировку, инференс через эти фреймворки. Вот. Сверху этого есть тоже экосистема различных EDK для каких-то конкретных доменов, есть Model Zoo, есть сервисы, которые позволяют нам автоматически под вашу задачу подбирать модели, тренировать для там, людей, которые не являются экспертом. Это вот Model Arts. Вот. И MindSpore здесь играет тоже роль вот такого полноценного фреймворка для тренировки, для инференса. Зачем его Huawei начал делать, да, там при наличии других популярных фреймворков? Ну, во-первых, всегда, когда вы ограничены архитектурой чужого решения, вам сложно раскрыть все возможности платформенные. Поэтому в этом плане MindSpore — это идеальный способ использовать именно платформенные возможности а, для тренировки, для инференса тех решений, которые хардварные есть от Huawei. Ну и во-вторых, э, у компании огромный, а, огромные команды собраны экспертов мировых в области AI, и очень много инноваций случается именно в самом софтварном стеке, которые позволяют даже на том же самом железе более эффективно выполнять там ту же тренировку. Я немножко про это расскажу. Буквально вот быстрый такой взгляд на то, как выглядит код в фреймворке MindSpore. Я думаю, для тех, кто там знаком с PyTorch, с TensorFlow 2.0, выглядит достаточно все похоже и понятно. Вот. И это один из плюсов MindSpore, то есть он очень легок в изучении, в использовании, вот, но при этом под капотом собрана там вся мощь и алгоритмическая, и платформенная, и этот стек позволяет эффективно все использовать. Если чуть более подробно про API говорить, то он в себя включает ну, такой классический набор инструментов, билдинг-блоков, которые вам позволяют работать с нейронными сетями, то есть создавать из каких-то типовых билдинг-блоков, лейеров, использовать этот инструментарий, чтобы ваши собственные лейеры на питоне реализовывать. Есть механизм автодифференциации, который позволяет ваши новые лейеры в режиме тренировки использовать. Там, соответственно, loss-функции, оптимайзеры и другие high-level building блоки, которые позволяют вам эффективно запускать тренировку, работать с датасетами, мониторить процесс тренировки. Вот. Соответственно, экосистема продолжает наполняться, развиваться. Есть Model Zoo вот, для перечисленного вида доменов, Computer Vision, NLP, рекомендательные системы, в том числе и MindSpore смотрит в сторону графовых сетей, reinforcement learning, то есть это современный фреймворк, который идет в ногу со временем. Есть также ряд уже приложений, которые используют, и под капотом есть много интересных техник софтварных, как я уже говорил, да. И еще важный момент, который стоит отметить, что не только, но на железе от Huawei это все можно запустить, то есть это все работает и на ЦПУ, и на ГПУ, то есть вы это можете устанавливать и пробовать, даже если у вас пока нет доступа к железу от компании Huawei. Вот, буквально еще пару минут про основные какие-то вот такие софтварные вещи, которые дифференцируют этот стек. То есть вот команда MindSpore активно проводила инновационные исследования с тем, как ускорить процесс тренировки. И вот они сделали уникальный оптимайзер, который использует оптимизации второго порядка для того, чтобы ускорить процесс сходимости тренировки. И вот по их замерам они достигли 20% ускорения по сравнению там, с типовыми оптимайзерами, которые в других фреймворках используются. Вот. Также внутри находится такой важный компонент, как Graph Engine, который обеспечивает оптимальное разбиение графа для его отгрузки на NPU, различные графовые оптимизации, фьюжены, минимизацию негативного импакта от различных конверсий, также обеспечивает работу с различными пресиженами и так далее. Есть, как я уже сказал, автоматическое дифференцирование примитивов, что позволяет вам свои примитивы добавлять и эффективно их использовать. Есть удобные и эффективные возможности использовать автопараллелизм как по данным, так и по различным карточкам и устройствам подключенным, и при этом это все с точки зрения семантики API легко включить и использовать. И также есть тулы, которые позволяют миграцию осуществить из PyTorch и TensorFlow в MindSpore. По поводу комьюнити, оно активно продолжает расти. Здесь какие-то вот ключевые факты приведены. Вы видите, что и там посещение страниц растет, и число коммитов, и число людей, которые за репозиторием следят, вот, и там видна география, да. Россия, к сожалению, еще не очень активно представлена, но мы надеемся, что вот через серию таких мероприятий мы роль российского AI-сообщества в этом фреймворке поднимем. Важный момент – это такой полноценный open source проект, в который вовлечено академическое сообщество, и китайские университеты представлены, и многие европейские университеты представлены. И мы призываем, я надеюсь, на сегодняшнем митинге есть представители университетского сообщества из России, тоже включаться. Я чуть попозже расскажу, каким образом. В рамках проекта есть 14 сейчас рабочих групп по интересам, и как они так по-английски называются, да, Special Interest Group. Вот здесь перечислены различные подгруппы, да, то есть это и фронтенд, компиляторы, Model Zoo, работа с данными, Graph Engine, недавно появилась MindSpore Lite, это для мобильных устройств. Вы можете все это найти в репозитории и включаться в работу. Сейчас эти группы возглавляют лидеры IT-индустрии, там, из университетской среды, из различных компаний, которые там, по принципам open source проекта действуют и развивают различные билдинг-блоки MindSpore. И здесь очень важно еще раз подчеркнуть, что это развивается по принципу open source проекта, то есть любой contribution, мнение, идеи, они очень важны, они будут обсуждаться, поэтому включайтесь. Вот, по поводу research проектов. Командой MindSpore было обозначено вот на данный момент 10 направлений, которые интересны с точки зрения research. Очень много, я не буду останавливаться на каждом, да, то есть спектр большой, все темы интересные, важные и находятся на, так сказать, острие исследовательских направлений, поэтому если с вашими тематиками исследовательскими есть какое-то пересечение, то есть возможность заявить вашу идею, использовать MindSpore как инструмент, там, расширять его возможности, чтобы для вашей исследовательской тематики это все было использовано. И эти проекты, они будут фондироваться Huawei компанией, и там, бюджеты начинаются от $500 000 на проект и может быть выше, там, в зависимости от сложности и сроков ваших исследовательских работ. Вот, такая есть возможность. Мы немножко спонтанно организовали первые мероприятия. Спасибо всем, кто подключились. Поэтому пока по контактам вот используйте мой e-mail. Если у вас есть какие-то вопросы, предложения по темам, то присылайте, пожалуйста, мне. Я сейчас еще в чате его напишу. Вот, по ресурсам, вот веб-сайт MindSpore, GitHub, и подписывайтесь на новости через мейлинг-лист. Introduction сессия на этом с моей стороны закончена, и сейчас я передам слово коллеге из Китая, который будет уже про TVM рассказывать. Давайте, может быть, там буквально 2-3 вопроса, если есть, и переключимся на следующий топик. Если нет, то сразу переключимся. Окей, тогда переключаемся. Okay, thanks everyone. Leon, you can switch to your topic and.
Oh, okay. Thanks. Can anyone hear me?
Yes, we can hear you well.
Okay. So wait a minute. Oh. Okay. Okay. So good morning and good afternoon to everyone. I'm Leon from Computing Open Source Technology Ecosystem Department. Today, I'm glad to share the topic about TVM and autokernel generator in MindSpore. So for the outline of this session, there will be 4 chapters. In the first section, I will give a simple introduction about TVM. And next, we will have a review view of autokernel generator library. And in the third part, we will show some AKG integration in the MindSpore. And then lastly, we will also share some experimental features developed in MindSpore community. So from this figure, this is the official framework architecture of TVM. So just as the official indication, TVM is an end-to-end machine deep learning compiler stack. So in as you can see in the top level, you can see multiple AI frameworks such like TensorFlow, PyTorch, and MXNet, such frameworks. And in the high level IR layer, we call it relay. It can import all the models from AI frameworks and lower the model into the TVM graph. And in this section layer called the tensor expression, this is the lower level of the IR expression. So for these two relay and tensor expression, we will explain it in the next slides. And in the third layer, we call it the target code generation layer. So as you can see, the primary goal of TVM is to generate the kernel for different hardware accelerators. For example, for the Intel series chips, we can TVM uses LVM library to generate the target code, and for the GPU and the mobile device chips such as iPhone, they can use a CUDA or Metal library. And as for other RISC series chips, there is a library called Versatile. In short, is VTA library to generate the target code. And in the right of this figure, it's the optimization for across the whole stack. So firstly, we will introduce and explain what is relay and TVM IR. So generally, relay is the high-level functional IR used to represent the module, the AI framework model or the computation graph. here are some design principles for relay. Firstly, it needs to support traditional data flow style programming. And secondly, it will also support the functional style scoping and light binding to make it as a fully featured language. As you can see this figure, if the TVM users use relay Python API to write the code, you can call some primitives in relay layer. For example, if you want to define a variable, you can call relay.var and input the parameters. And for some basic function, you can directly call the function defined in relay. In this example, you can call the log. And also here in the third line of the code, it means the relay can add the log function and also between the log function and the v1 itself. Lastly, it means it will create a function class to wrap the whole process. So if we input the Python code into the TVM, and for the text form of TVM computation graph, you will find there it's a function about the log function and the add function. And if we transform the text form into AST structure, and you will see the relationship between each primitive function. So that's how TVM use relay primitives to construct the whole computation graph. And for the TVM IR, it's the low-level programming IR, which means it will not define the whole computation graph. Rather than it, we can use the TIR prime func class to represent the function, the low-level function. And it can also be transformed by TVM IR passes. So since TVM has relay and the TVM IR two levels IR, so what's the relationship between the in a word, a relay function can be lowered into multiple TVM TIR prime functions and a top level function that acts like an index of those TVM IR functions. And the next is the part of VTA stack. So for the VTA means versatile tensor accelerator is just a library that transform the AI framework model into the RISC-like programming chips. And as you can see, if you want to compile the AI frameworks model into other chips, you can use the VTA stack to extend the hardware to achieve the code generation work. And the next, I can show you the whole compilation flow from the top of TVM. Firstly, if we pick a model from the AI frameworks such as TensorFlow, and firstly, a TVM has a part called import. So through the import layer, the AI framework model can be transformed like a relay function. As you can see, we can use relay dot function, the method to describe the relay function, the relay computation graph. And the next, we can use some primitive function scheduling to transform the relay IR module into TVM IR module. And in this layer, we can also use some TVM IR passes to optimize the whole pipeline. And on the right of this layer, it contains several TVM IR or prime function method. And on the lower layer called target translation, it means we can, through TVM, we can further lower the TVM IR module into the target code. Take some CPU, for example, you can use LVM to use LVM to generate some binary code. And you can also use CUDA to generate the GPU target code. And for other hardware device, you can use a VTA stack. And then lastly, if we want to load the target code into the runtime environment, we can use runtime module method to load the target machine code and provide some instance to the caller module. So that's generate the compilation flow. And
Leon, sorry, this is Dennis. I have a question about a previous slide.
Okay.
So the question is about auto TVM. Does it make scheduling at the level of functions rather than at the level of, I don't know, lower primitives like individual instructions? So can you please elaborate a little bit more about units of scheduling?
You mean this auto TVM?
Yes, yes, correct.
So I'm afraid I'm not quite familiar with its inner design and implementation, but from what I know, it acts when we try to build a relay graph, and if we want to lower the relay graph into the TVM layer, just like if we want to split the whole graph into some primitive kernels. So that's what auto TVM acts. Which like in some auto turning scenarios, I guess.
Mm-hmm. So then, you know, it seems quite, I don't know how to say, unusual that for the purposes of such scheduling, relay is used, which is high-level representation, as you mentioned, and not TIR, which is lower level. But okay, probably this is, you know, next level of details that can be discussed, you know, kind of offline. Thank you.
Okay. So shall we move on?
Yeah, please do. Please go ahead.
Okay. Okay. So after we compare the model to the target code, we can deploy it and even integrate the binary code into the runtime environment. So currently, for the TVM runtime, it supports almost anywhere. You can use it with JavaScript, with Java, Python, and C++. For the mobile device, it supports the Android and iOS, and even some browsers. Okay. So next is about the auto kernel generator. So firstly, I will introduce some motivation of this library. So currently we are facing some challenges about operator development. Firstly, with the time development, there are more and more large networks coming up. So there comes the growth of operator requirements. And secondly, so traditionally, if we want to develop an operator, we will develop the operator implementation with C or C++. So, but for the massive operators development, it's very low efficiency to develop all the operators. So if we can develop a automatical kernel generation mechanism, then it will be much higher efficiency. And for the third challenge, in some auto-parallel, in some auto-parallel scenarios, it's difficult to schedule the operator manually. So if we can use some automatical mechanism to schedule the operator automatically. And lastly, for the operators, it's not support for all hardware accelerators. If we want to support more accelerators, we have to develop another plugin. So for the compiler stack, it will be easier to develop a common compiler stack to extend the hardware device. And that's how the autokernel generator comes up in MindSpore. And for then I will introduce the overview of AKG. So generally, AKG is formed with these 4 layers. On the top layer is the operator representation. So for the AKG users, it can develop the operator based on TVM computing DSL language. As you can see from the code, if we want to develop a softmax kernel, we traditionally we need to use C or C++ to develop all the details of hardwares. But now with the TVM, we can for the TVM user, it only needs to write the high-level language expression using TE library. And as for the low-level instruction details, it would be no worries from the users, and users can just write several lines to generate the high-level, high-performance operators. And in the second layer, it's called the IR standardization. That's because from the TVM DSL, it can be transformed with the TVM IR. And then next, we can use some polyhedral technology to automatically scheduling the kernels. Lastly, we will generate the CCE target code automatically using the CCE plugin in TVM. And this is the framework of auto kernel generator. Firstly, is the normalization layer. The goal of this layer is proposed to formulate the fused operators because currently there are some constraints if we apply the polyhedral technology into TVM. So we before we apply polyhedral process, we need to normalize these operators first. So as for the detailed process, I will skip in this topic. And in the auto schedule part, as I said before, currently we use polyhedral technology to automatically schedule all the fused operators. And after auto schedule, it's the instruction emit. And in this layer, we will so all the fused operators will be transformed and lowered into CCE level code. And for the backend IR layer, it will act as the low-level optimization for the CCE code. And lastly, it will generate the CCE target code. So now we have know what is AKG, but how AKG is used in MindSpore. So I will introduce in this section. So before we see the AKG integration solution with MindSpore, I will give an initial description about MindSpore framework. So generally, MindSpore framework can be divided into three parts. Firstly is MindSpore front-end expression. In short is ME. And in the second layer is called MindSpore graph engine. We call it GE. And lastly is the backend runtime. And for the overview of this integration plan or solution, basically that's what graph kernel library works like the bridge between MindSpore and AKG. So for MindSpore, when the graph kernel flag is enabled, so the kernels will be reconstructed in the graph level. So in this case, there would not be some specific differences between graph and kernel. They will both described with the MindSpore subgraph primitive. And this new kernels described in the will be described in the JSON format. And if you look at these orange arrows, firstly, we will call the kernel build method to build all the fields kernels. And for the graph kernel library, it will call the compare with the JSON method to build the fields kernel and generate the JSON file. And okay.
Sorry, Leon. Sorry for interruption. This is Dennis again. Okay. So, could you please give an example of operator which is not reconstructed and the same operator which is reconstructed? Because I'm still struggling to understand what is the reconstructed and not reconstructed operator.
Okay, you mean the code level?
Yeah. You mentioned that you know, when graph kernel flag is enabled in MindSpore,
yeah.
Operators are reconstructed. I don't quite understand what is reconstruction. So I'd like to ask you to give an example of reconstructed operator and not reconstructed operator.
Okay. This is just an overview. I can explain it later in the later slides.
Okay. Thank you.
Okay. So and in the left blue arrays, after we build the kernel, and MindSpore will call the launch function to launch the kernel and run it. So so that's the general code flow between MindSpore graph kernel and AKG. But from the view of MindSpore users, it will only use one flag to control the whole process. That is enable graph kernel. So from MindSpore API, if we want to enable the graph kernel features, you can just set the context like the code shown. If we use enable the graph kernel flag, then the fields kernel predefined in the MindSpore will be enabled to automatically generate with the graph kernel. So as for the inner implementation, as you can see, if the user enable the graph kernel flag, then we will on the MindSpore front end expression. So this is mainly defined for the kernel development, kernel developers. If we want to develop some fields, the operators, we can use the graph kernel DSL language to develop the fields kernels. as you can see, this is how we develop a graph kernel fused operators. And when we use a graph kernel DSL to build the fused operator, so it will come through the basic operator fusion, and next will execute the shape and the data type inference, and then it will compile the because in MindSpore every all the model or the operator will be expressed as with the graph. So in the third part, it comes to the graph compile step, and after the graph compile, it will switch the code flow according to the configuration of your the kernel, configured. So if your kernel is white box kernel, it will switch to the compute DSL code gen part and call compute DSL from AKG. If you configure it as a black box kernel, it will switch to TBE to generate the TBE kernel.
Sorry, Leon, might be I missed. What is white box kernel and black box kernel?
I think it's just a specific term for the kernel types. So how can I explain it? So you can consider it as this is A and this is B. So before we develop all the kernels, we will design a list to distinguish all the kernels which can be designed as a white box kernel and which are not. For the white box kernel, they can be designed as the fused kernels, and for the black box, we don't suggest it to execute the fused kernel, I guess. Yep.
Okay, probably later on we will need some examples, the follow-up materials to highlight the benefits of both approach and which one is recommended in which case. And we can provide such information later on.
Okay.
Maybe with some illustrative examples.
Yeah, I think more precisely, it's not about a technical question, but for the white box kernel, it will developed by the some team, by one team, and for the black box kernel, it divided by another team. Yeah, and we can go on for the MindSpore graph kernel code flow. So so if we, for example, we develop a sigmoid white box operator, and firstly it will pass into MindSpore expression Python API, and as you can see, it's the MindSpore pipeline to lower and transform the operator defined with users. Firstly, we will get the parser step to pass the Python primitives to generate the Python AST. And the next, after the parser step, all the Python code will be transformed with the MindSpore IR. And next is the abstract specialized means. So for this layer, it remains the Python AST. But if we, after the abstract specialized, it will be transformed with the pure specialized IR. Means it has nothing relevant with the Python primitives, but it acts the same function as the Python code. And after that is the optimizer and the source code transform. We can also call it autodiff to generate the differentiate the graph. So as you can see, this is the picture of generated sigmoid fused operator IR graph. Actually, that's the ANF-IR expression. So through this graph, we can form the concrete relationship with the Python code we defined. And next, for the after the backend step, it will generate the kernel tasks. And then for each kernel tasks, we'll call build kernel function. And then it will call auto AKG to generate the binary code. Yeah.
Sorry, I want to ask one question. This field IR graph is this field IR graph is generated automatically, or maybe by some manual some ruler.
These graphs are all generated automatically.
Okay, you mean based on some mathematical or algorithm, right? Or maybe some.
Okay, so take some example. If we do some Python coding, and we can transform and lower the Python code into the LLVM level. If we print the LLVM code, you will see all the low-level code to like logical machine code. So this IR graph is more like that style.
Okay? Yeah, I know the cell. Yeah. Okay.
And so that's the general code flow about developing a white box operator and build the that is the compilation workflow.
Sorry, may I ask questions? This is Alexander Filipov. Maybe that's a very sorry for the questions where it's very like maybe technical. On the graph on the right side, we expect to see the optimized code, right? My question is why we see doubled the tensor 1.0. It should be like common sub-expression eliminations there. Suppose we should use one tensor in two places.
You mean this one?
Yes, this one and to the right and to the up another one, the same one. That means that
I guess you can see this line of code sigmoid equal 1.0 divide expression. I guess
my notion is that the code is not optimal.
Sorry, I didn't follow you.
Alexander, probably first of all, it may be not supposed to be fully optimized code. You know, the title of this section just claims that it is fused graph. No, not fully optimal. This is the first one. The second one, we don't know, you know, conditions for you know, for memory here. Might be it is more beneficial still to have these two tensors are not used because of restrictions for, you know, for the memory. So on and so forth. So it's hard to judge.
Okay, but just in pipeline, which was shown on some of previous slides, there was a notion of common subexpression elimination. It's a very first stage, without any taking into account any memory and something else. So
I see. Understand.
That should be eliminated. Okay, sorry for that question. Please continue.
Good question.
Okay. So as you can see, if for the fused operator IR graph, it can reduce 60% computing overhead compared to the non-fused operator graph. Yeah, and that's how AKG. That's how AKG improve the performance of executing the whole graph. Okay. So I think that's all about AKG and TVM. And in the last, I'd like to share some experimental features in MindSpore community using TVM. So firstly, I will introduce to you the new technology called WebAssembly. So from the official indication, WebAssembly is a stacked virtual machine based on binary operation instructions. In the first day, it's used in browser. And as we all know, in the browser scenario, typically we use JavaScript to develop the code. But as we all know, JavaScript is very slow. So some scientists think up a method to transform other source code to build the WebAssembly binary code and load it through WebAssembly runtime into the browser, and that can accelerate all the code greatly. And with the time going, actually the WebAssembly is not only fit in browser, but we can use it into the non-web scenario, such like servers and IoT use case. And from this figure, you can see where WASM lies between the program and the compiler and the device. So if we use C++ or Rust, this IR means LLVM. So actually, WASM is a logical target code for the LLVM. It lies between LLVM and the physical hardware device. So that's why one of the great features of WebAssembly is very portable and security. So that's the solution of we propose to TVM community. It's like we can leverage the TVM compilation stack and also use the WebAssembly runtime to compile MindSpore model and load it into different runtimes, just like TVM.
So quick question. So is there a way to serialize a MindSpore model to Onyx?
Yeah. So currently, because MindSpore doesn't support be transformed into relay directly. Yeah, so we have to use ONNX to be the bridge.
Okay. And is there a plan to expand set of converters and contribute with MindSpore support to TVM relay converter?
Currently, there are no plan for that. But
Okay, so we plan to leverage ONNX
yeah.
as intermediate step.
Yeah. Because it will be the minimum code development. Yeah. And through the TVM compilation stack, we can because WebAssembly is officially supported by LVM backend, so we can directly use TVM to generate the WASM type code, target code of this model. And in the runtime cases, environments, we can load the graph through WebAssembly runtime. And because of the portable feature of WASM, we can load it into different scenarios, like a browser, IoT, and even the server. So if you are interested into this solution, here is the link to TVM community. And actually, for the previous slide, it's not our final goal. So for the next step, we are planning to use reuse the AKG compilation stack and do not use TVM anymore, or we will use part of TVM defined in AKG. So the final framework would be like we can directly call the MindSpore Python API and generate the WASM code. And in the MindSpore runtimes, we can reuse the AKG runtime and the WebAssembly runtime to load the kernel into different runtime defined in MindSpore. So imagine that we can develop many kernels once, and they can be loaded into anywhere in browser and the cell phone and the server. I think that's the final goal of our for this experimental feature.
Okay, that sounds interesting for sure.
Yeah. So if you are interested, you are all welcome to join in this solution.
So you presented the link of kind of base solution which you plan to reuse for this diagram, for this architecture. Is it also developed in open source and part of AKG repository in MindSpore?
Yeah. And actually, it's in the design phase. So if you are interested or you have any other ideas, we can develop it together.
Okay.
May I ask you questions?
Okay.
Sorry. I was raising a hand, but if we can ask questions just like this, is it okay?
Yes, go ahead.
Okay, sorry, I didn't quite understand how AKG is related to auto TVM. So the TVM schedule optimizer, is it synonyms or are these two different approaches, or these are two different layers of the same approach?
I think that's a good question. So sorry for I didn't explain it previous. So as you can see for, sorry. Okay, for I think it's for this figure. Actually, when AKG call kernel build function, actually it calls the TVM to build the kernel.
So it calls auto TVM. I mean, the auto TVM, the model which finds optimal schedule.
Yeah, I think. Sorry. I think,
probably not. I think calling build and calling after TVM is two different things inside TVM.
I think AKG currently don't use auto TVM feature in TVM. Instead, it uses polyhedra to implement the auto schedule process.
So it's kind of different approach. From writing a TVM mod, from getting model into TVM and calling auto TVM. This is different from using AKG.
I think the reason is actually TVM is developing rapidly. So in the last release for 0.6, we actually AKG used the last release of the TVM, and at that release, auto TVM is not mature, and so AKG is built on TVM and reuse some of TVM features to provide the auto kernel generator feature in MindSpore. And another difference is, as you can see, TVM has relay, right? But for AKG, it doesn't use the relay layer at all. It is only use the tensor expression layer.
Okay, thank you. So I understood that this is a different approach, because auto TVM, yes, it uses relay, and it requires you to explicitly define scheduling search options.
Yeah.
And here it looks like you do not do this.
Yes, you are right.
Yeah.
Okay, thank you, Leon. I think it was a good introduction for TVM, and probably in terms of how it used in MindSpore, we still need to look through the code to understand it a bit better, and maybe some practical examples will be helpful in the future, and we will follow up with people and provide some examples maybe through GitHub repository. That's it for today. Thank you for joining, and we will keep you informed regarding our further plans. And like I said at the beginning, we are very much interested to form active community around MindSpore in Russia. So your questions, comments are welcome regarding the topics. Did we dive too deep at the beginning or not? What kind of topics you want to discuss and cover? So feel free to approach me with your feedback, and I am looking forward to meet next time. Maybe we will organize another session in 3 or 4 weeks from now, and I will work with Zipeng and our colleagues to come up with an agenda, including relying on your input to make it productive. So thank you very much, and have a good day.
Thank
Bye.
you.
Thank you.
Ilya.
Bye-bye.
Bye.
Thank you.
Thank you. Bye.